Hello and welcome to the coronavirus edition of the fifth lecture from our signal theory class. On the previous lecture, I talked about filtering in the spectral domain. I told you that we can take the spectrum of our signal, multiply it with the frequency characteristic, and get the altered spectrum. And by doing this, we can, for example, suppress power noise interference or get bass and treble of our music adjusted. I also showed you that this is equivalent to computing the convolution in the time domain. I can take the input signal, compute the convolution with the impulse response, and get the filtered signal. Today we will view this operation as a signal passing through a system. At the input of a system, I put my signal X, and at the output I get my signal Y. What the system does can be described like this. In the time domain, the system computes the convolution of the input signal with its impulse response, which in the spectral domain is equivalent to the spectrum of the input signal being multiplied by the frequency characteristic of the system. So, to describe this system, I can either provide the impulse response or the frequency characteristic. I can use either because one can be computed from the other with the Fourier transform. Just a side note, under some mild assumptions, which we will talk about later, a system like this would be a linear time invariant system, or an LTI system. I have mentioned LTI systems on the first lecture, so now you can see that we are getting to them. But at this point, it is just a side note and we do not need to dwell on linearity and time invariance of this system. Instead, here I have a few additional results from the previous lecture. Remember, when we fit a filter a Dirac delta pulse, we get the impulse response of the filter. Now, instead of a filter, we are talking about a system. So here we will talk about the impulse response of a system. But this means that the convolution of the Dirac delta pulse with any impulse response is the impulse response itself, or more generally, the convolution of the Dirac delta pulse with any function is the function itself. You actually had this for the homework, so tough luck to those who did not do their homework. When you take this equation into the spectral domain, you get this. The Fourier transform of the Dirac delta pulse is 1, and the Fourier transform of the impulse response is the frequency characteristic. So, by feeding the Dirac delta pulse into the system, in the spectral domain, I'm actually feeding the system with all the frequencies. So, in the output spectrum, I will see how the individual frequencies are being passed. That is, how they are amplified and phase shifted, which is exactly what the frequency characteristic is. This is actually a way how you can get the frequency characteristic of a system. You can feed it the Dirac delta pulse, measure its impulse response, and the Fourier transform of the impulse response will get you the frequency characteristic. Actually, this approach is a tad theoretical. It can work a bit with discrete systems, but with time-continuous systems you may have a small problem generating that infinitely narrow and infinitely tall Dirac delta pulse. So especially with time-continuous systems, we usually measure the frequency characteristic by other means. But at minimum, you should understand the principle of getting the impulse response and frequency characteristic. Other important thing to understand is this. Firstly, the Fourier transform of this is this. So when I take the Fourier transform of a convolution in the time domain, I will get the multiplication in the spectral domain. I have written that here. The Fourier transform of the convolution becomes multiplication. The same can actually be shown for the continuous time. The Fourier transform of the convolution becomes multiplication. Now you can say this in reverse. When in spectral domain I have multiplication, I will have convolution in the time domain. So the inverse Fourier transform of the multiplication is convolution. Now, do you remember those formulas for the forward and inverse Fourier transform? They are actually very similar. You have a different sign here and some scaling, but other than that, this is pretty much the same formula. So it should not surprise you that when you crunch the mass, it turns out that similarly to the inverse Fourier transform, when you take the forward Fourier transform of a multiplication, you will get convolution in the spectral domain. So the Fourier transform of the multiplication is convolution. There is actually one small exception. When you take the Fourier transform of discrete signals, you will end up with convolution of their spectra. However, there is a small change in the definition integral of this convolution. Normally, we would have this integral from minus infinity to plus infinity. But because these spectra are periodic, we cannot integrate from minus infinity to plus infinity. The integral would not converge. But when you crunch the math, it turns out that if these signals are periodic, the convolution is computed over one period only. This type of convolution is called a circular convolution, and we denote it by a circled asterisk. It is computed from periodic signals, and we integrate over one period only. The overall moral of the story is that the Fourier transform always connects multiplication and convolution. When you take the Fourier transform of one, you will get the other. The linear convolution is applied when what you convolve is aperiodic. The circular convolution is applied when what you convolve is periodic. Okay, at this moment your proper question should be, why should I care? What is it good for me that the Fourier transform of multiplication is convolution and then the Fourier transform of convolution is multiplication? Well, this property becomes handy in many situations. Right now I will show you how you can use it for practical real-world spectral analysis. Here I have a very simple example where I have a sine function and I would like to compute its spectrum. I will start with a trivial but rather unrealistic case where this sine is continuous in time. On the exercise I showed you that the spectrum of the sine function are two Dirac delta pulses. The sine wave is a pure tone, so in the spectrum all its energy is on a single frequency. And if anybody shows me this spectrum, I have no problem reading it as a spectrum of a sine. Okay, but when you record your signal, it is not going to be time continuous. When you record a signal, you have to sample it. So, what happens when you sample this signal? Well, you get this. This is a sampled sine. Now, what happens in the spectral domain when I sample my signal? Well, in this case, not much. The frequency lowercase omega will become the normalized frequency, and where I had the sampling frequency, I will now have 2 pi. And the spectrum will become periodic. This period will repeat itself. So when the signal gets sampled, the spectrum changes a little, but if I know how to interpret it, I'm okay. But this is not a completely realistic case. If I sample a sine, which is an infinitely long signal, I will get an infinitely long sequence of numbers, and that you are not going to process in MATLAB. So in real-world recording, in addition to sampling a signal, I need to cut my recording and sample only a finite number of samples. I need to cut this signal to a finite length. But if I cut my signal to a finite length, will it not change the spectrum? Well, it will, and not for the better. So now let's take a look at what happens when I cut my simple signal to a finite length. To be able to understand this, we need to describe that cutting to a finite length mathematically. And mathematically, we can describe this cutting as a multiplication of this infinitely long signal with a function like this one. This function we call a window, and it is 1 where I want to keep my signal and 0 where the signal would not be recorded. When you multiply this signal with this window, you will get this, and when you compute the discrete Fourier transform of this signal, these zeroed values and these zeroed values will not contribute to the computation, so as if they were not there. Thus, I have cut my signal to a finite length. So mathematically, I can describe cutting of an infinitely long signal to a finite length by a multiplication in the time domain. And now comes what we have learned earlier. What happens when I take the Fourier transform of this multiplication? Well, it will become a convolution in the spectral domain. In this case, the circular convolution, because the spectra are periodic. So while I multiply these two signals in the time domain, in the spectral domain I have to convolve their spectra. This is the spectrum of my sine, and this is the spectrum of this discrete pulse. We have actually computed this on the exercises. So now we need to find out what happens when you convolve this with this. Well, let's take a look at what happens when you convolve a function with a Dirac delta pulse. This is my function, and this is a Dirac delta pulse sitting at omega naught. This is the definition integral of the convolution. Now you need to use the sampling property of this Dirac delta pulse. This Dirac delta pulse sits at omega minus omega naught, so the result will be this function at omega minus omega naught. Essentially, convolving a function with a Dirac delta pulse will shift the function to the position of the Dirac delta pulse. And what if we have two Dirac delta pulses? Well, if you write the definition integral of the convolution, you would see that this can be broken to first convolving the function with the first Dirac delta pulse and then with the second Dirac delta pulse. So if you convolve your function with two Dirac delta pulses, your function will get shifted to the position of these two Dirac delta pulses. Let's use this in our spectrum. I have two Dirac delta pulses in one period from minus pi to pi, and I will convolve them with this function. So this function will get shifted to the position of these two Dirac delta pulses. Once it will get shifted here, and once it will get shifted here. So this will be my final spectrum. This will be the spectrum of a sine function when it gets sampled and only a finite number of samples is recorded. So this is a spectrum of a sine you can record in real life. And you can see that it looks distinctly different from the spectrum of that infinitely long time-continuous sine. This peak is no longer an infinitely narrow and infinitely tall Dirac delta pulse, and you can see these side lobes where there should have been nothing. Both of these non-idealities can cause trouble. Firstly, these side lobes. These look as if they were leaking from this main lobe, so they are called spectral leakage. And the problem with spectral leakage is that it can cover some weak signals that would otherwise be visible in these parts of the spectrum. I can have some strong signal at one frequency, and there can be a weak signal at some adjacent frequency, and this spectral leakage could easily cover that weak signal so that we would not see it. We will take a look at this case on the exercises. Now, what can we do to suppress spectral leakage? Well, where do these side lobes come from? Well, they come from these bumps in the spectrum of this window. And why do I have these bumps in the spectrum? These bumps are some high frequencies. So what part of this window can create high frequencies? Well, high frequencies are not going to come from these zeros or from these ones. High frequencies are generated by a fast change. In this window, this sudden change and this sudden change is going to generate high frequencies. So if I want to get rid of the high frequencies in the spectrum of my window, I need to get rid of these sudden changes, and I need to make my window smoother. For example, I can use a window like this. This window is much smoother, and you can see that its spectrum has much less high frequency content, and consequently the spectral leakage is much less pronounced. There is still going to be some, but this is much better. So the moral of the story is that if I compute a spectrum of a finite length signal, which is what you always do in a real world, you are going to get spectral leakage in the spectrum. Spectral leakage from strong components can cover weak components, and that is a problem. Therefore, to get rid of the spectral leakage, we do not just compute a spectrum of a signal with finite length. When we have a signal with finite length, we weight the signal with a smooth window, and only after we compute the spectrum with the Fourier transform. When you do that, the spectral leakage will be suppressed. So, in MATLAB, prior to the DFT computation, you need to multiply your signal with some window. MATLAB will generate some windows for you. We will check them out on the exercises. Now, there is another problem that we will have to face when we work with a finite length signal, and that is the problem with so-called spectral resolution. Here I have an example similar to the previous one. The main difference is that now my signal is not a single sine, but two sines at different frequencies, say omega 0 and omega 1. In the time domain, it is rather hard to see that this is a mixture of two signs, but in the spectral domain, you can clearly see this. Now, what happens if I measure this signal in real life? I have to sample my signal, so the spectrum becomes periodic. Not a big deal. And I have to record only a finite number of samples. So the final spectrum will now be given by the convolution of this ideal spectrum with the spectrum of my window. And as before, this spectrum gets shifted to the position of all these Dirac delta functions. But because this main lobe is pretty wide, all those shifted copies of this spectrum add up and I will get this. Two peaks came here, one at omega 0 and one at omega 1. But when they added up, they created just a single blob, and now I can no longer see that there were in fact two signs in the spectrum. I can see just one blob. In this situation, we say that we do not have sufficient spectral resolution to distinguish these two frequencies. Now, what can we do to improve our spectral resolution? Well, our problem is that this peak is too wide. And how can we make it more narrow? We had this previously. This peak will become more narrow when this window will become wider. Let's check it out. If I make this window wider, which essentially means that I record a longer signal, this peak will become narrower, and presto, now I can distinguish my signs at different frequencies. Now I will switch back and forth so that you can see how the spectrum changes when I use shorter or longer signal. You can see that the longer signal gives me better frequency resolution. Now, just to finish this is a very ugly spectrum, full of spectral leakage. So to get rid of that spectral leakage, I will change this rectangular window to a nice smooth one. Now I have much less spectral leakage, but the spectral resolution is not exactly fantastic. The problem is that this smoother window has wider peak in its spectrum. So to get back the spectral resolution, I have to use even longer signal. And when I do that, I will get a spectrum I do not have to be ashamed of. So regarding the spectral resolution, we have found that the longer the signal, the better the spectral resolution. Turns out that the spectral resolution, that is the ability to distinguish two frequencies that are delta f apart, is always worse than 1 over the length of the signal in seconds. So for example, if your recording is 1 second long, you will not have better spectral resolution than 1 Hz. If your signal is 100 milliseconds long, you will not be able to distinguish frequencies that are closer than 10 Hz. So this was some useful information where the convolution allowed us to understand some important properties of spectral analysis. Now we will get back to our filters and systems. Again, from the previous lecture, we talked about the finite impulse response filters. If the impulse response of my filter is finite, then in the convolution formula, I need to sum only finite number of non-zero values of this impulse response. So this formula simplifies into this, which can be written like this. Last time, we just called this a convolution. Today I will add a new name. For an FIR filter or an FIR system, these two equations also go under the name difference equation. It is just another name how to call this. Now on the previous lecture I showed you that you can draw this formula as this schematic and that these multipliers correspond to the impulse response. Today I will also use an alternative name. These values of h of m are sometimes denoted as b sub m, and they are called filter coefficients. So in an FIR system, the impulse response and filter coefficients are the same. And oftentimes you can see this schematic to be drawn with filter coefficients instead of the values of the impulse response. This is the same thing, just different letters. Also, on the last lecture I showed you how to find out what the filter does when you know its impulse response. You can compute the Fourier transform of the impulse response, which will give you the frequency characteristic, and from there you can judge whether it is a low pass, high pass, or whatever pass. But what if you want to do the inverse process? What if you are dreaming about your very own low-pass filter with some very specific frequency characteristic and you would like to realize it as an FIR filter? For this you need to get the impulse response. But how are you going to get that? Well, you could reverse this process. If the frequency characteristic is given as the Fourier transform of the impulse response, then the impulse response could be found as the inverse Fourier transform of your dreamed of frequency characteristic. Will this work? Well, sort of. Here, I have an example of this design process where I will show you what problems you are going to face. You start in the spectral domain and you specify your desired frequency characteristic. Here you wish for low pass that will pass everything from 0 to some frequency omega naught. You can see that I'm doing this in the continuous time spectrum just to keep things simple. By the way, the frequency band where I pass my signal is called the pass band, and the frequency band where I do not wish to pass my signal is called the stop band. Now, to get the impulse response of a filter with this pass band and stop band, you need to compute the inverse Fourier transform of this frequency characteristic. If you do the actual computation, you will find that the impulse response of such a filter is sine x over x function. Now, can you use this impulse response? Well, no, because of two things. The first problem is that this impulse response is time continuous, and for an FIR filter, we would need it to be discrete. But we can sample this impulse response and we get this. When we sample, the spectrum will change. It will become periodic, but that is something that we have got used to by now. Now, can we use this impulse response for our FIR filter? No. The second problem is that it has infinitely many non-zero values, and that is just not going to work for a finite impulse response filter. So we need to cut this impulse response to a finite length. And how do we do the cutting? Well, mathematically, the cutting can be described by a multiplication with a window. So to get a finite impulse response, I need to take this infinite impulse response, multiply it with this window, and I get this. But what happens in the spectral domain? What happens with my frequency characteristic? Well, if I have a multiplication in the time domain, I'm going to have a convolution in the spectral domain. So to find out what will be the frequency characteristic of my filter, I have to compute the convolution of this ideal characteristic and the spectrum of my window. This is rather hard to do from the top of your head, but it will probably not surprise you that these side lobes will somehow find their way into the result of the convolution, and I will get the frequency characteristic like this. Note that this frequency characteristic is quite different from this ideal but unrealistic case where the impulse response is infinite. This result actually troubles me. Here, in this stop band, where the frequency characteristic should have been 0, I do not have a 0. So these frequencies that should have not been passed are going to seep through, and the filtering is not going to be perfect. This is actually bad enough so that we do something about it. And what do we do about it? Well, the source of these bumps are these bumps, which we can get rid of by replacing this window with a smoother one. When we do that, these bumps are much smaller, and so are these. So now the filter suppresses unwanted frequencies much better. So when you design your filter, you do not just compute your impulse response, sample, and cut it to finite lengths. To get good suppression of unwanted frequencies, you need to multiply your impulse response with a smooth window. That is why this design procedure is called the window method. Once you get your final impulse response, you can do your filtering. You will use the values of the impulse response as the weights of the filter. Here you will feed your input signal. This filter will convolve it with the impulse response, and here you will get the filtered signal. Before we finish this off, it is worth noting that this frequency characteristic is rather lame. Ideally, it should have this brick wall shape, but instead we have this slow transition from passband to stop band. Now we have this transition band. How could we improve it? Well, this slow transition is actually caused by excessive width of the spectrum of my window. If I made this pulse narrower, this would actually become steeper. And we do know how we can make this pulse narrower, don't we? We need to make this window longer, which actually means that we need to use longer impulse response. When we do that, we get longer impulse response, this peak becomes narrower, and this transition becomes steeper. So by increasing the length of the impulse response, the frequency characteristic of our filter gets closer to the ideal shape. If you want to get really close to this ideal shape, you may need to use a very long impulse response, sometimes hundreds of samples, sometimes even thousands. But this very long impulse response can cause some trouble. When I have a very long impulse response, I need to do a lot of multiplications here. And all of these multiplications I have to do in each clock cycle. To compute this output, for every n, I need to do these m multiplications. And if m, that is the length of the impulse response, is large, the computation can be very demanding. Now remember that this m we also call the order of the filter, or the order of the system. And that is why we say that an FIR filter can have a very high order, in which case it can be computationally demanding. Okay, so we may need a very long impulse response to get a good frequency characteristic, but we do not want to do a lot of computations to get it. What can we do? We can do the following trick. Let's have one more look at the FIR filter. This is a second order FIR filter, except it is drawn sideways. The impulse response of this filter is just 3 samples. When you feed a Dirac delta pulse to this filter, for negative time, this delay line is full of zeros and the output is 0. At time 0, number 1 comes here and the output is B0. Then on the next clock cycle, the number 1 comes here and the output is B1. And on the next clock cycle, the number 1 moves here and the output is B2. On the next clock cycle, that number 1 is simply forgotten, this delay line is full of zeros and the output is 0 again. So our impulse response is just 3 samples. Now what can we do to extend our impulse response without adding more delays and more multiplications? Well, we can add these feedbacks. Now if I feed a Dirac delta pulse here, the number 1 will get fed into this delay line, but after 3 clocks it will not simply fall out of this delay line and be forgotten. Thanks to these feedbacks, it will be scaled and fed back to the filter, so some numbers will keep circulating in this filter indefinitely. And this will create an infinite impulse response with a finite number of multiplications. The order of this filter is still given by the number of these delays, which is 2. So with order 2, I was able to create a filter with an infinite impulse response. I created so-called infinite impulse response filter, or an IIR filter, or if you prefer, an IIR system. Before I show you an example of an IIR filter, I just want to point out that these constants A0, A1, A2 are so-called coefficients of the filter. More specifically, these coefficients B are called feed-forward coefficients, and these coefficients A are called feedback coefficients. You can see that the feedback coefficients are used in this funny way where we multiply with negative value of these coefficients. And at this place we even use the inverse of the coefficient A0. At this point, do not worry about it much. You will see that it actually simplifies some math later. Now let's take a look at an example of a simple IIR filter. Let's investigate what this filter does. To examine this, we need to find its frequency characteristic, and for that we need to find its impulse response. So what is the impulse response of this filter? Well, imagine that you feed the Dirac delta pulse to the input. For negative time, there will be zeros everywhere and the output will be 0. At time 0, number 1 comes here, so at the output I will get number 1 as well. In the impulse response, at time 0, I will get this number 1. Now on the next clock cycle, this number 1 shifts here and 0 comes at the input. After this multiplication, I will get 0.5 here, to which I will add 0, and I will get 0.5 at the output. I will get this 0.5 at the output. Now on the next clock cycle, this 0.5 shifts here. It gets multiplied by 0.5, which gives me 0.25. To this I will add 0, and at the output I will get 0.25. I will get this 0.25 at the output. And this process repeats itself indefinitely. At each clock cycle, the previous output is multiplied by 0.5, so I will get this impulse response. Mathematically, I can write this impulse response like this. And you can see that I was able to create an infinitely long impulse response using a very simple IIR filter with order 1. Now this impulse response I can use to compute the frequency characteristic by computing its Fourier transform. Here I have substituted my impulse response and I can rewrite this expression like this. And I can now see that this is actually a sum of this infinite geometric series. At this point, you should recall the formula for the sum of infinite geometric series and recognize that I get this. So this is the frequency characteristic of my filter. Now I will take this frequency characteristic into MATLAB, plot it, and I will get this. The blue line is the frequency characteristic of my filter for this coefficient minus A1 equal to 0.5. You can see that it is a sort of a low-pass filter because those low frequencies are amplified more than the high frequencies. In this plot, I have also plotted frequency responses for different values of the coefficient A1. You can see that for higher values of coefficient A1, I get steeper and steeper low pass that more and more amplifies low frequencies. To get such a sharp frequency characteristic with an FIR filter, I would have to use a very long impulse response, which would be computationally demanding. With an IIR filter, I can do this with order 1, and in this case, a single multiplication per clock cycle. Okay, now you may ask, if the IIR filters give us infinite impulse response with fewer computations, why do we even bother with FIR filters? Well, IIR filters have one significant drawback. Let's take a look at what happens if I set this coefficient to 1.2. This impulse response will change to this. The impulse response will now be rising exponentially above all limits. You can see the problem even in this schematic. If this coefficient is greater than 1, then the value circulating in this filter is getting bigger and bigger after each clock cycle. If this coefficient is greater than 1 and you feed such filter any non-zero signal, its output will likely diverge to some infinity and the filtering will not work. We say that in this case the filter is unstable. And this is the drawback of IIR filters. They can become unstable. At this point, you should object that if I do not want this filter to become unstable, then I should not set my coefficient minus a1 to be greater than 1. Well, sometimes you cannot help it. The problem is that these filters are computed in a computer, and computers cannot represent numbers with infinite precision. A computer has just a given number of bits to represent a number, so in a computer a number can have only a limited number of decimal places. So for example, if you set some filter coefficient to be pi, the computer can never work with exact pi, it has to round it. In this specific case, it is rather unlikely that a coefficient like 0.9 would be rounded to 1.2. The rounding errors are typically much smaller. But with higher orders, nothing extreme, just for example something like 20, the IIR filters become very sensitive to even the smallest changes in their coefficients. So even if your computer rounds the coefficient at the 10th decimal place, it may be enough for your higher order IIR filter to become unstable. And that is why sometimes we actually prefer FIR filters. Even with rounding errors in their coefficients, they can never become unstable because they do not have any feedbacks. The last thing left to do is to explain the difference equation of an IIR filter or an IIR system. Remember, for the FIR filter, the difference equation was just the computation of the convolution. It was an equation that describes how to compute your filtering. For an IIR filter, we also need an equation that describes how to compute our filtering. How can we do this? We will start with the schematic of an IIR filter. Now we will split this line of delays into two. This is actually the same thing as this. The value here is the same as here. So it does not matter if I have this line split or not. But if I split my delay line, here I can actually recognize two filters. First this one and then this one. And I can say that this filter has some frequency characteristic h1 and this filter has some frequency characteristic h2. Now when I filter my signal in the spectral domain, I start with the spectrum of my input signal, then I will multiply it with the frequency response of the first filter and then the frequency response of the second filter. This will give me the spectrum of my output signal. Important thing to note here is that the multiplication is commutative. Therefore, I can multiply in reverse order. I can first multiply with h2 and then with h1. In this schematic, that means that I can change the order in which these filters are applied. I can first filter with this filter and then with this filter. I can do it like this, and I will get the same result. This is actually an important fact by itself. If you put two filters in series, their frequency responses will multiply and you can change the order of these filters without changing the final result. Now we will use the change order of these partial filters to write the difference equation of this entire IIR filter. First, take a look at this first filter. That is just an FIR filter and we already know what its difference equation is. The output of this filter, which I have denoted here as U, can be computed like this. How do we compute the output of the second filter? Check it out. The output is given as 1 over A0 times this sum. So here I will write 1 over A0 times this bracket into which I will put the sum. And what do I sum? Well, this U of n, that goes here, then I have minus A1 times Y of n delayed by 1, that goes here, and minus A2 times Y of n delayed by 2, that goes here. So the difference equation for the second filter is this. Now, if you combine these two equations, you can compute your filter. In this form, you would write these equations into a computer, and this is the form that is used, for example, in MATLAB. In mathematics, we rewrite these equations so that they are less practical for computation, but they look nicer. I can rewrite these equations like this. First, I will multiply this equation by a0, so this a0 will come here, and then I will move these terms with y of n to the left-hand side. On the right-hand side, I will leave only u of n. And for u of n, I will substitute this. As a final result, I get this equation. This equation is written for the second order. The highest delay here is 2. For a general order m, we can write this equation like this. And again, these a's and b's we call the filter coefficients. These b's are feed-forward coefficients and these a's are feedback coefficients. And m is the order of the filter, which corresponds to the number of delay elements in the schematic and to the greatest delay in our difference equation. In MATLAB, you can implement this very simply. You define a vector of feed-forward coefficients, a vector of feedback coefficients, and then to compute the filter, that is to compute this difference equation, you just use command filter. This is your input signal, and the returned vector is your filtered signal.